Okay. So I assume everybody can hear me. Just tell me if there's any problem in the chat. Good. So yeah, so I trust you guys can see this transaction model and transaction models and concurrency control. Let's see if I got the right one here. Yeah, the right one. Okay. Another thing just a couple announcements. Recitation number 3 is posted. And that involves this transaction stuff. So I can maybe, if we have time permitting, I can kind of just go over quickly what I expect out of that. And that's due exactly in 1 week. So we're going to hold recitation next Tuesday. There is no lecture on Friday this week, but instead I would like to kind of at least touch base with all the projects. So if you guys want to have a meeting on Zoom, project meetings, then just let me know. But what I want out of every project at least is basically some kind of status report from the leader. Doesn't have to be much, just kind of something that indicates that you guys are working on things, that you're making some progress on your projects. So just kind of a status, like maybe 250 words. Just no big PDF documents needed or anything, or really just a quick description of kind of whether you're on track, whether or not you've had to make some changes to the requirements. If you have new ideas and you want to, just kind of what the status is. So the thing is that you're not obligated. It's not like a contract in this course. So you're not obligated to live up to all the conditions, everything you said you were going to do in the project description. We're not going to go back and look at that and say, oh, did you deliver on what you said you would? So you can make big changes if you wish. But it'd be nice to hear us about, if you've made some decisions about that, to hear them or to have it so that you describe them in this note. And then also, if you want to discuss things and just kind of have a chat on Zoom, then Friday there's a conference I'm going to, so I'll be kind of occupied all Friday, but tomorrow or Thursday, and then probably Friday early, very early, or Friday very late, I could probably squeeze something in. So even next Monday. So if you guys want to try, just let me know if you want to chat about your projects. Okay, so those were the announcements. Any questions? Looking at the Zoom chat, and I see there are none so far. Okay, so let's go on now. And today, what we're going to talk about is multi-version concurrency control, which is kind of the modern way this gets done. If you recall, last time we talked about just like the single value concurrency control, the classic stuff. So what did we cover last time? We covered things like just a definition of what it means for transactions to be serializable. So remember that's kind of a critical thing. So transactions are serializable if they are equivalent in some sense to a serial schedule. So if you look at a set of n transactions, and you look at the actual mix of the interleaved operations, if you could separate those out so that you make it into some ordering of those n transactions, that means it's serializable. And then if you recall, the notions of how that gets defined is there's the truth, the kind of the ground truth of what serializable is, and that has to do with view serializability. So that has like a nice logical definition about two schedules are view equivalent, view serializable equivalent, if they all have the same initial reads. Every transaction does the same initial reads. The reading from a write of one transaction that remains invariant, and the final writes are all invariant. Then it's view serializable. The problem is that it's combinatorial to kind of find out if to actually looking at one particular schedule and determining whether it's view serializable is actually a combinatorial problem. So what that means is we relax back to a different notion of serializable, which is actually that we can compute and we can kind of control for, and that was this notion of conflict serializable. All right, so conflict serializable. What that allows us to do is that allows us to say that well, if something is conflict serializable, then it's also view serializable. But if something was view serializable in some intricate way, conflict serializability might not see it. Okay, but we settle with conflict serializable, and then what we introduce is the notion of well, then we say, okay, that's just what the theory is telling us. Then there's the issue of kind of how do we implement this thing, and then locking strategies tend to be what get used. And then if you recall, we had two-phase locking, which means that you acquire all your locks in a growing phase at the beginning of the transaction, and then you release the locks. So you grow them monotonically up, and then you do your work and everything, and then you release them monotonically down. So you don't go, you grab locks, you release locks, and you grab locks. That's not going to be a two-phase locking. All right. So two-phase locking, actually, if you follow two-phase locking, then you're going to be guaranteed that you're going to conform to the schedules that get produced by regulating things that way are going to be conflict serializable. So you kind of get that as a guarantee, which is nice to have. One of the problems, of course, is that if you release the locks in a gradual, you don't hold locks up to the very end of the transaction. You release them gradually. What that means, you can start releasing them. Somebody else can grab release one of your write locks. So you've written something. Somebody then gets a read lock on that, and they start reading it, but then you abort. So, what that basically means is that you did a dirty write, right? And that's really not good. So that conforms in the classic notion. That conforms to this notion of a read uncommitted. So when you can maybe run things under isolation level, read uncommitted. But the problem is that might necessitate a rolling. If you really want to maintain consistency, that might necessitate rolling aborts, rolling. You say the rollback, kind of cascading rollbacks. That's not good. And although maybe in certain applications you just kind of let it go and accept this might be something that you would. There's certain cases in which you would do that for performance reasons because it's a lot cheaper to kind of do it that way. To have, the less strict the isolation level, the better performance you get. So there is a trade-off. There's a lot of things. There's trade-offs, but so generally speaking, what we do when we talk about two-phase locking, we say that you have to hold the lock to the very end because we don't want to kind of trick around with this durability property because that means that we won't have durability in the transactions. So then there's the issue of what we do in the growing phase, and this idea of being able to grab all the locks a priori is not realistic because a lot of times in a transaction you don't know what it actually is that you're going to be getting your locks on because you're maybe doing some reads and then you find something that you want to do a write to, and then you want to get a write lock, but you wouldn't know that beforehand. So a lot of times we just kind of accept the fact that we will acquire our locks in a gradual manner. This, of course, opens up to deadlock, so you can have deadlocks as a result of that. All right, so all of that was, that's all kind of like the classic way you look at things with transactions, single value concurrency control, where you have one database and transactions all around that are trying to get access to that database, and they're doing it through these locking protocols, right? So they're locking things, and then they're in some cases, so the controller sometimes has to abort them and these kind of things. So that was kind of how things were, and that was in the original case of SQL, that was kind of how things were defined. And based on that, what you wind up getting kind of a natural set of anomalies that then get guarded against. And then we have the isolation levels of SQL, and the classic isolation levels of SQL are basically you read uncommitted, which allow for dirty writes and dirty reads. You read committed, which means that excludes the dirty writes and dirty reads. Just to back off for 1 second. So what then does read uncommitted give us? Well, it gives us we don't have the lost update problem. Okay, so it gives us something. We don't have transactions clobbering the values of their transactions. So we don't have the anomaly of a lost update. But under read uncommitted, we can have the dirty read. Then we get into these kind of more esoteric ones that have kind of fallen by the wayside now. We'll see in the modern approach. These are this basically a repeatable read, and then let's see. There's read committed, then there's repeatable read, and then there's serializable. So this repeatable read. There's several levels in there, and basically what it is, it's something we're going to cover in any kind of detail. But basically what it is that like, if you do a read again, do you always see the same state of the database? Now it might be under like read committed. If you do another read and somebody else had committed, then you'll see the new version. And then this under this repeatable read, it's like you don't see that. And then, but there's a notion that you can allow for phantoms, and phantoms are kind of an artifact of this locking granularity. If you go back to the slide, you see that it's kind of an artifact of the locking granularity, where you kind of lock a range, but then if you reissue the query, so you have all the tuples in the range locked, but if a new tuple sneaks into that range, and then you re-execute the range query, that new tuple will show up. So that's a phantom that's coming in. It has to do with how the locks are being distributed. But it doesn't really show up in the modern systems anymore because of the way things are actually getting implemented, which is something we'll cover today. So that was a quick review, just verbally, of what we covered last time. And now what we're going to get in today is, I think, a bit more useful because it's kind of going to be talking about how things are actually getting done now. So this will conform, if you play around with PostgreSQL and see how it does its transactions, you'll see it reflected in today's lecture as opposed to this more background lecture that we had last time. Okay, so the theory is this kind of single value concurrency control, and most current systems are using this multi-value multi-version concurrency control. So why is it using this multi-value concurrency control? And the reason is because really it used to be too expensive to implement this, but now because memory, both primary and secondary, has become less expensive and faster, etc. We can play this kind of game of multiple versions rather than doing this having one single version that's getting locked. So it does require a lot of memory, but it's kind of an elegant way of doing things, and it's kind of it is the modern way of doing it. So let's go over what it actually is. Okay, so let's do this kind of carefully. So let's just. I'll just try to kind of give a lot of supporting verbal to kind of understand, to kind of clarify these concepts. So let's assume that we have so I mean, just intuitively think of it this way. Think of it, let's say that we have really a lot of memory. Okay, so here's what we're going to do. All right. So let's see here. Well, I don't know if I should include people's names here, but if I just have first names, I don't think it'll be a problem. So let's say we have Matthias and we have Tony. All right, we have a database. All right, Matthias wants to work on the database and Tony wants to work on the database. So here's a possibility. I'm global, right? Okay, so I have the global true value of the database. So Matthias wants to work on it, Tony wants to work on it. And so what I do is I give them both a copy of the full database. Here, have the whole database, right? Well, okay, thanks. So now they have the full database, right? And now they're going to do their operations on that database, right? They're separate copies. Now, once one of them is done, let's say that Tony is done first, right? And Tony changed the value of a couple tuples in some strange table. And so then Tony sends, oh, hey, I'm done now. He says, oh, okay, thanks, Tony. So he sends me back the full database. So he was perfectly isolated because he's just working on the database. And he sends me back a full copy of that database. And then I look into it and I say, oh yeah, he changed this tuple and he changed this tuple. So therefore, I'm going to take those changes, I'm going to integrate them into this global database, right? So now as that's going on, I'm integrating them in there, all kind of in there. Then Matthias comes back and says, well, I'm done with my copy of the database. And so again, he has the full copy of the database. He has made his changes. He sends them back in. I say, oh, you made some changes. And then as it turns out, he makes changes to tuples in a way that don't conflict with what Matthias had done. So I just integrate those versions in as well. Okay, so that's multi-version concurrency control. So I mean, in principle, now in practice we don't do this because it'd be crazy to copy the full database. But in principle, they're both getting a copy of the database, right? Now, if it turns out that, let's say that just in this very simple case, let's say that Tony gives me the updates and makes the changes, fine, and then Matthias gives me his copy, and then there is actually a conflict. In other words, there was something that Matthias had written, and then Tony wants to write over it. I'm sorry, Matthias wants to write over it. Tony made the changes. Say, okay, sorry, Matthias. I'll give you a fresh copy. You're gonna be aborted. I'm gonna give you a fresh copy of the database, maybe, and then you can make the changes there. And now that fresh copy, of course, will have the changes that Tony had made. So then, then we're getting this kind of, notice we're getting a serial. Then basically the serial schedule we're getting then is first Tony, then Matthias. Okay, so that's kind of in principle what's going on with this multi-version concurrency control. That's kind of the most intuitive way I can describe it. So if anybody has any questions, hopefully that registered a bit. But that's kind of maybe the intuition. Maybe not so accurate because we're going to get the details here now, but that's kind of the intuition of what's going on. So now let's talk about really how this is going to be done, because we don't be copying the whole database and sending it over. That's crazy. We're not going to do that. Okay. So instead, what we're going to have is we're going to have basically these pointers, and we're going to have these different versions. So let's say we have a version of X. X is some data value, some tuple. And then we have a version of Y, which is also a tuple, and then a version of Z here. So we always have a pointer to the global. All right, so we have this pointer. Global basically points to what is the current and unique database state. Right, so this is ground truth of what the database state is. Now, each of these transactions, transaction A, B, and C, and transaction C and D and all that, they all have their own little local versions of Y. So when you look at this, then you say, well, what is there is no local version of, so if you look at like D here, there's no local version of X. Therefore, what that means, it means that basically what D, that transaction D, is looking at the global version, okay? So anytime you do you're gonna get a write lock, basically. You're gonna be, you're gonna wanna be writing something. What you're gonna wind up doing is you're gonna wind up creating your own local copy, all right? That's what the transaction will do. So transaction A, B, they all have the different versions. Okay, now let's look at this example here. So the example is that transaction D is going to read Y, so it creates Y right there, and then it's going to write Z. So their version of Z here, this version here of Z, transaction D wants to write that, okay? And this version of Y, transaction D had read. Okay, so actually it looks in this case where we basically say if you read it, then it becomes part of your local copy here. Okay, when the transaction commits, TD has done this, and then when the transaction commits, so TD wants to commit, then its local writes now become the new committed version. So if we look right here, its local writes, what did it write? It wrote Z. Okay, so now look here. Z, which was right here, so this was its local version of Z, right? Now global points to that. So global is now pointing to the local version of Z, right? Okay, fine. So now when local is pointing to Z, then what that's going to mean then is it means that the older version of Z, which was part of which was the global version, is just basically put on a garbage dump. All right, it's basically sent off to a garbage collector. All right, and we'll see later on what that garbage collector in SQL is basically vacuum. So ultimately you're going to vacuum that up, but it's just kind of a dead tuple. All right, it's a dead tuple on the table. So yeah, it's memory's cheap. Yeah. So all right. Then it's local read only copy. So it had done a read. So basically in this case, I think I misspoke earlier about at least in this example here, that reads are being turned into local copies here. So this read here, this guy right here where he did the read, that also becomes garbage because now he's done. He's already, it's finished with. Okay, so basically, yeah, so all these garbage is going to be, so we have garbage here and we have garbage there. That's all going to be recycled via the vacuuming process. All right, so that just talked about kind of modifying something and then committing it. So if we talk about insertion though, so let's say that basically now we're going to talk about inserting a new object. So we have, let's say that we have this object X, which is now going to be inserted, a new tuple. Just for purposes of argument, say we have transaction A and B, and they both want to do the insert. But let's just say the transaction A does it first. So transaction A is going to do the insert, right? So that means, it just means that now we're going to have a global pointer that's going to point to this new version, right? So this, or not new version, but this inserted tuple. So it's created. So now global points to something that's new. B, of course, is going to have trouble here. This is probably going to result in, this is going to result in probably some abort. Because when B tries to commit, then it's going to be, if it's the same value, maybe, but it's probably, in this case here, B is very just unlucky, right? Created the same thing. So maybe with the same key value or something. All right. Now, that was insertion. So we did modify and commit, insertion, and now let's talk about deletion. So deletion, so let's say here now we basically say that transaction A is going to delete the object X, so it's going to just be deleted. Okay, so all that means then is it just means that at commit here, then this right here is just going to get turned to garbage. Right? So it's the dead tuple. That's because it got deleted. Again, B is going to have problems when B tries to commit. All right. So that's kind of, you're showing how you're doing this more with pointers now. So you're not, so this whole kind of, that silly example I had where you're copying the whole database over it's actually partially correct, because if you do, in this case here now, if we're creating versions for the local copies and you do like a, table scans, you're going to get all that copying over. So you're going to create a lot for the garbage collector later. But if you're just kind of going to do reads over a certain part of the database, and you're going to be doing writes in that part of the database. Now this pointer kind of playing around with these pointers now has it so that the whole thing doesn't, we're not copying the whole database back and forth. But there's a fair bit of memory being used here. Okay. All right, so that's kind of the foundation of how modern concurrency control works. This is this multi-version approach. All right, so why, then the question might be, well, why do we even study the single value concurrency control? Well, it gives us some kind of theoretical foundation for understanding what, just kind of notions of serializability. And it forms kind of a reference model because it's well understood. I mean, it's kind of the classic way of looking at things. And then also because of most of the multi-value concurrency control implementations are using locking, and thus this earlier stuff we're talking about locking is going to kind of transfer over. In fact, we're going to say that it's going to be pretty clear that under multi-value concurrency control, what's going to come up in a second is that we're doing it under 2PL, two-phase locking. All right. The version-based version of multi-concurrency control, the basic idea is that there are many versions of the database out there, but there's only one true version, but versions are being distributed around to different transactions. One of these is the global database reflecting just the committed updates. Okay, so the global database, the one true database, is the one that is reflecting all the committed what did I say here? Well, the committed transactions, the committed updates to the database. So the non-committed versions of the database are just private. This is kind of a perfect isolation model. They're private to the one single transaction. Uncommitted updates by transaction TI are reflected only in the private version of things. So as you do your updates, so before you commit, you do your updates, it's only happening over your private version of the database. And then the reads, however, when you do the reads, that is something that is, there is kind of like, there are two fundamental isolation levels under multi-value concurrency control. As it turns out, we're going to see there's going to be three. It's kind of it's a tricky issue, but there's going to be three different isolation levels that are going to emerge under multi-version concurrency control. So under the read committed, then you can actually, as you're going, you're not perfectly isolated under read committed. And then there's going to be what's called snapshot isolation, which is, until recently, was the kind of the strongest isolation level. And then we're going to have serializable snapshot isolation, which is the new one, the third one, which has kind of an interesting story behind it. Okay, so the two fundamental modes for multi-version concurrency control is the snapshot mode, right? And then the read committed mode. All right, so snapshot mode is basically a snapshot of the whole database is taken when it begins execution. So in principle, the moment you as a transaction begin, you get a snapshot of the database, and that's what you're going to see throughout as you work with the database. Of course, you might change it, so it'll drift from what it was initially based on the updates you're doing to your private copy. But you see the snapshot at the moment you started. Okay, so basically that you just read and write from the snapshot through the lifetime of the view, and then in the end you're going to commit it, and hopefully it'll go through. Isn't always the case. So then there's another one, which is this read committed, which is a more relaxed one. So this one you back off from this full snapshot isolation. And in this one here, you read all the data objects which the transaction has not yet written. So if you haven't touched them and written them, then you're always going to be reading the latest version of those. So you're going to read the latest committed version of those back from global, right? So, but once you write something, then that value is going to be part of your private version, and you'll no longer see any other version that was committed. Of course, if there was one that was committed, then you're kind of in trouble because you're going to have a hard time integrating back in when you do your commit. So you're probably going to abort. But that's, you know, it's the risk you take as you if you're a transaction. So this read committed corresponds basically to this read committed of the classical read committed under under single value currency control. All right, so let's look at this read committed. So suppose that this transaction I is operating in the read committed isolation. Okay, so I'm a transaction I'm under read committed. All the reads are made from the unique current committed version of the database. Okay, so we're always assuming there's another transaction running at the same time. So this actually is changing under the hood as we go. Writes are only made to the private database, which is associated with me as a transaction. If I get aborted, so if I either self-abort or I get aborted for some other reason, maybe for deadlock or something, then this private version I was maintaining is just poof, thrown on the garbage heap. Okay, it's just turned into garbage because I got to restart. Okay, so it's but then if I commit, so I made changes to the right. If I commit, then this needs to be integrated to the database. Okay, so how do we manage this? We kind of have two fundamental ways in which we're going to manage this process. So basically, two transactions are going to be an update conflict if they run concurrently. So they're overlapping in time, and their private versions contain at least one update to a common object. So so in that case, where we had Tony and Matthias both are running. They're both going to update tuple X or something, and then they both make changes to that, and now they both want to commit. Okay, so one of them is not going to be able to do it. All right. So a very easy way to do this is basically to say the first committer wins. So it's basically, and that was kind of what I modeled when I was doing the example, because it was like, well, both Matthias and Tony want to change X, the tuple X, and what was it? Tony came in first. So Tony basically came in and said, well, here are my changes. And I said, great. And I integrated his changes, right? So he won because he was the first one to commit, his change. So there's no lock required. It's fine. So no action is taken until he's ready to commit. And then when the global version of the database is checked to see whether there's any, okay. All right, so if there's a, okay, so when Tony does it, it's fine. When Matthias does it, I look and I say, oh, did you just make any changes or something? No, well, somebody beat you to it, so therefore you are aborted. Okay, so you get aborted. This is a very simple kind of way to implement it. So there's another one. So that's first committer wins. And then there's the first updater wins. Okay, so this is actually what gets implemented. This is what PostgreSQL will be using. So basically, what it will say is something like this. It says that, well, the what you want to do is you wind up getting write locks. So basically, there's going to be, now we're going to institute locks on the objects. So let T and I be transactions. In this protocol, a transaction write locks data objects which it intends to update. Okay, so what happens in this case is that Tony comes in, and then what Tony does is, because he wants to, they both start. They both get their own private version of the database. And then what happens is that Tony basically says, I want a write lock to this object, X. So I say, okay, I'll give you a write lock on this object. Okay, so now they're working under a locking protocol. So Tony has a write lock under the object, and then if Tony now what happens is then later on, just a split second later, Matthias wants a write lock, and I say, wait. Okay, now, because it could be based on separate reads, or it could be reading the object and writing the object. Basically, what happens now, if Tony continues on now and Tony commits, then I'm afraid that I have to abort Matthias. However, if Tony actually aborts, then I can grant the right lock to Matthias. Okay, so it allows for a little bit different. It allows for kind of a waiting process on these objects. Okay, so now you might say, how often is Tony going to abort? Well, we don't know. I mean, the thing is that in some cases it might be something like this, like we have a particular implementation where Tony has a certain budget time to get his work done in. If he can't get this work done in that, we're going to abort him. Right? This is kind of this classic example of like, well, I mean, what you don't want. Okay, so what you don't want is you don't want Tony like basically taking the right lock and then waiting forever on and kind of like just basically wasting time. Meanwhile, everybody's waiting on him to kind of finish. So you might just say, well, you got a certain amount of time, and if you don't get it done in that time, then you're just going to get aborted. Okay, and then that would then allow for Matthias to continue. All right, so it's there are some advantages to having this kind of locking type strategy. Let's see here. So yeah, so that just kind of this is a case where we're doing locking, and we're basically saying the first one who gets this called first updater wins is the basically it has to do with the first one who's going to grab a lock to make the update. All right, so that was just kind of like talking about we have a definition here of what read committed was or is under multi-version currency control, and then we just talk a little bit about how conflicts are handled. Okay, now let's turn on to snapshot isolation. Okay, so snapshot isolation. Let's see, let's turn the time. In snapshot isolation, yeah, they both get copies, basically private copies of the database that they can't be. They're kind of perfectly isolated. All right. So when they're ready to commit, then they basically just write their local version back. So this is typically realized versus a locking strategy. Okay, so you typically do some kind of locking when you're doing your writes on the objects inside of snapshot isolation. You'll see this when you do the exercise with PostgreSQL. Okay, so snapshot isolation. Interestingly, so snapshot isolation. So I'll agree with that SI. So basically, you're not going to have dirty reads because after all, you only read at the beginning of the transaction. So you're reading from the committed version of the database, right? By definition, you're not going to have non-repeatable reads because you're only you're perfectly isolated. You have a snapshot of the database, so you're not going to have a situation where you have phantoms or this kind of tuples kind of sneaking in as other people commit. So this is at least as great as those provided by read uncommitted, of course, and read committed. Okay, it's also strictly stronger than repeatable read. Right. So therefore, actually, technically, it satisfies the conditions of serializable because in the SQL standard, because the SQL standard again only talks about the absence of anomalies to reach certain isolation levels. All right, but there are anomalies which can occur. There are anomalies that can occur in snapshot isolation which cannot occur in true serializable mode. All right, and this is a bit of a surprise. I don't know exactly the story that happened in the industry when they discovered this, but basically what it meant is it meant that people, a lot of like PostgreSQL before version 9.1, when you wrote it, when you ran it under serializable isolation level, it actually wasn't serialized. It could give you schedules that weren't serializable. All right. And as I was talking about before, is that allowing for that allows for kind of those with kind of malicious intent to kind of maybe screw around with the state of the database. All right, because they're always going to be looking for an exploit if there is one. Okay, so here's kind of the anomaly that comes up. It's called write skew. Okay, so let's assume that we have the following situation. We have X and Y representing the balance of two distinct accounts, right? And then we have an integrity constraint which says that, and you can do this with triggers, right? Which says that the sum of those two accounts has to be greater than or equal to 500 euros, right? It has to maintain that. So we have two separate accounts, and they start out with 300 apiece. So that's 600. So yeah, that's greater than 500. That's fine. Now we have two transactions. One is going to withdraw 100 euros from X, and the other one is going to withdraw 100 euros from Y, right? And they're both going to check this constraint, right? This constraint, well, are we maintaining a total balance of 500? All right. So both are going to read both the values of X and Y. All right. So that's the first thing they're going to do. They read X and Y. And then one of the transactions is going to take 100 from X, and the other one's going to take 100 from Y. So they suppose they both get snapshots in the beginning of the transaction. Okay. So each then is going to run without the knowledge of what the other does, because they're both have a snapshot isolation. They have isolation. So actually, as it turns out, the final state that we get of the database is going to be 200 euros in X and 200 euros in Y, which actually violates this integrity constraint, right? So that's not good. That's violating this. That's technically violating this C in ACID, right? So the schedule that does this doesn't involve any dirty reads. There were no dirty reads. There was no non-repeatable reads or phantoms. So it passes the isolation levels for read uncommitted, read committed, and repeatable read. But it's still this weird. It's allowing for the database to get into a weird state. All right. So write skew cannot occur with true serializability. So with true serializability, so if you're going to say, all right, fine. In a true serializability, remember, under true serializability, either transaction, the way we model it is that it has to be equivalent to transaction T1 running and then T2 running, okay? Now, if we did it, or T2 and then T1, if we did that, let's say we had T1 run first, it would check, it would say, fine, we have 600, I'm gonna withdraw 500, I'm gonna withdraw 100 from account number Y, account number X. Now then transaction 2 says, okay, ooh, well, we have only 500 there now total, and if I withdraw 100, now I'll violate the constraint, so I won't do it. So transaction T2 in this case would not run. It would see that this is going to produce an undesirable state, and then by symmetry the vice versa, with T2 going first. So that would never happen, right? So it would never get into a final state of 200 if they were running concurrent, if they were running in a serial schedule, right? So therefore, but snapshot isolation let it through. So that's not good. So that is definitely an anomaly. Here's another way of modeling the anomaly, a little bit more kind of technical. Assume we have a ring. So just think of this intuitively. Let's say that we have a set of data values, all kind of, and we have transactions that are going to copy one from the other. So let's say that we have the value, an initial state, we have the value 1 here, the value 2 here, 7 here, 14 here, 5 here, and 6 here, all right? Now, what each of these transactions do is they'll read this value and they'll write it into that spot, into the next spot going along. Now, if they form a ring, if you think about it intuitively, if they form a ring, then some data value is going to get squashed. Some data value is going to get squashed in any serial ordering, right? What ordering would you pick? If they form a ring, what ordering would you pick to execute the transactions so that no data value gets squashed, right? This is the whole kind of thing of, we know intuitively if you need to swap, like, I mean, if this was just like if this was basically this one here, and this one here, then we're basically in that classic example of how do you exchange the value in two variables without having a third kind of bucket variable. I had a student once who said he called it the goldfish. Anyways, it's stuck in my head for some reason though. It's like, that is when you're going to be putting a goldfish from one tank to another. Anyways, but his dad said, where does the goldfish go or something? But it was something, it was kind of funny, but it stuck in my head. But anyways, you guys know, like if you're doing bubble sort or something, right? And you have the value, you got to exchange the values in two parts of the array. You have to exchange the values at two different indexes in the array. You have to have like a little temporary storage, right? To kind of stick the other one, because you're going to clobber it, right? So that's exactly what's kind of going on with this in this case here. So under snapshot isolation, actually, it will just kind of let you do it. But basically, we know that there's no serial schedule that would allow you to do it. So snapshot isolation actually will let you do it, and it'll do it right. But there's no serial schedule that will do that if it forms a ring. There's no way, So intuitively, then you should know that something's going wrong. Something that, wow, snapshot isolation can make that change. Well, yeah. But there's no serial schedule that could do the same thing. Therefore, snapshot isolation must be producing schedules that are not serializable, right? That's what's being just illustrated here. So it has nothing. This is an example here. Actually, what we're doing is we're showing that even more fundamentally, there's not that it's not serializable. So there's no integrity constraints here about this right skew thing where, where we have some kind of integrity constraint that needs to be maintained. In this case, it's just a pure direct kind of data reads and writes example that's showing that snapshot isolation is going to be is going to give you stuff that is not serializable. Okay, so this was a bit of a scramble then, because this kind of, let's see, I think we're just going to muscle through here, or maybe we'll take a break. I don't know, in the chat. Oh, I'm sorry, I missed a question in the chat here. Does that, I think this is, does that mean that there will be a lot of congestion where many people have to wait for one transaction? Yeah, see, that's the reason why you put, a lot of times you put timers on these things if you're doing it in a really kind of high throughput environment, that the transactions, that they'll get aborted if they taking too long. I mean, the thing about the locking, like one might ask, so why not just it'll be a lot simpler to implement it with just like first updater wins. Maybe there'll be cases in which you want to do that. The thing about it is that with locking, a lot of times, I mean, you'll at least kind of see that if you get wedged up, I mean, if you get delayed, maybe you abort yourself. It's just, you don't want to like run all the way through a transaction at the very end, get aborted. And then there's also the issue of like when you get restarted. Well, you have these prevention of live lock. So when you get restarted, you might get restarted with some priority on the locking, so that you'll have priority to grab the lock. So that the older you get, the more likely it is you'll get the lock. But these are all things that get fiddled with, and this is, it's very particular to the particular application that needs to get supported. Because what you're looking for is high throughput. You want serializability and high throughput. Okay, let's see. So should I just muscle through? Because I mean, I think that we could finish this, or we could take like a 5-minute break. So what do people? Does anybody want to take a 5-minute break? You can say it privately in the chat, and then if so, we'll do it. Maybe it's best we just take a 5-minute, and then we can resume. Yeah. Let's, because I mean, I don't want to go too long without a break. So yeah, let's be back here then at 11:05. And then we'll just resume this. And we'll probably finish early. Maybe I'll go over the recitation a little bit, so to get you guys aware of that. Okay, so we'll be back in 5 minutes, and I'll just stop the share here, and I'll pause the record. Okay, yeah. So let's. Looks like we can start up again. Gotta share the screen. Okay. So I trust everybody can see this. Just say something in the and everybody can hear me as well. All right. So yeah, so it's kind of remarkable that this kind of snuck through in some sense. But once it was recognized that, I believe it came out of academia. This was actually some academics were the ones who identified these problems, or at least brought them fully to the surface. Anyways, there was kind of, well, they had to fix it, make it so that it is truly serializable. So that basically kicked off an implementation effort to basically guarantee serializable snapshot isolation. So multi-value concurrency control, yeah, you're going to keep that, but now we want to make sure. Okay, let's prevent these anomalies to kind of creep in, these new anomalies to creep in. So that's basically this SSI, serializable snapshot isolation. All right, so so it's an optimistic approach that is a kind of lets transactions do their business, like go about things, and then looking for certain structures called dangerous structures in the direct serialization graph. So we're gonna look at that. We're gonna revisit this direct serialization graph. All right, so these dangerous structures are they occur when we have a snapshot isolation that's non-serializable, but it might also be that it's a little bit maybe it's a little bit overzealous in terms of so it's not sufficient. So in other words, if you see these dangerous structures, it doesn't mean that it's not serializable. But every time that it's not serializable, you do see these dangerous structures. So basically, if you see these dangerous structures, then what you do is you abort a transaction. You pick a victim. You have to pick a victim, and then you abort them to remove the dangerous structure from the DSG. All right. So your controller basically will be looking for dangerous structures, and if it sees them, then someone's going to get aborted. All right. So it's been introduced into PostgreSQL, and presumably all the other snapshot isolation models have something similar. All right, so the direct serialization graph revisits. Let's just look here. Remember what this means. Okay, so we basically have the three different conflict types. We have write read, read write, and write write. Those, read reads aren't. But basically, what if you go here, basically it comes down to like, why is there a write read conflict between T1 here and T2 over X? That's because T1 must write X, yeah, and then the next one to read X is then transaction 2, and that's correct. So that's the reason why we have this arc in the direct serialization graph, right? So we look at these. So we're building up this as things progress here. We're building up this DSG. We're building up this graph, right? Yeah, and then write. Why is there a write between? Okay, so there must be right here. We have a write of X by 3 and a write of X by 4. So there must be a write pointing from 3 to 4, and from 3 to 4 there's a write on X. Yeah, okay, so that's it covers all the you can kind of see it's pretty clear how this gets built up. All right, so so these are the possible conflicts that we're going to have, but okay, of the three types though, the only one that which may occur between concurrent transactions is a read write conflict. This is the only one that can happen under snapshot isolation. So if you put it another way, if X is a data object, and then at least one of if we're under snapshot isolation, and let's say that X is a data object, and let's say we're going to look to write read, and we're going to look at write. If those existed and I and J were concurrent, this will lead to a contradiction, that they can't be concurrent if those are in the DSG. And let's consider why it is. Okay, write is immediate, since concurrent transactions are running under SI may not write the same data object. Okay, so yeah, so it's going to be yeah, I mean, they're in the serial schedule that comes out, they're not going to be allowed to. So one of them is going to be taken away. Write read, basically, since the read occurs when it starts. So if some other transaction writes the object, but I do all my reads in the beginning, then by definition that transaction needed to actually done its commit before I started. Therefore, we can't be concurrent. Okay. Yeah. So basically, a concurrent again means that they overlap in time. If there's a write or a write read, then these cannot be. This is essentially repeating what we just said. I should actually move that slide there. So T1 must commit before the transaction J. Transaction I must commit before transaction J to see it's right. Thus, read writes can't be there. All right. Anyways, so let's. So basically, what we're looking at here then is we're looking at the one transaction. The one thing that can happen though is we can have a read write. Okay. So I have a transaction. I read a bunch of data, and then concurrently there's another one who actually writes some of the data that I read in the beginning. Right. So that's basically a read write conflict. Okay. So these are the ones that can actually occur. Right. So a dangerous structure in the DSG is simply this. It's basically just a sequence. So in the DSG, it's a sequence of read writes, okay, because these are the only ones that can occur anyways, of two consecutive vulnerable edges, which may or may not form a cycle. So it doesn't matter. I, J, and K here can all be distinct. All right. And the star here means it can be over data value X, and it can be over data value Y. Okay, so any of these things happening is going to be basically called a dangerous structure. So once you see a dangerous structure, then someone's going to basically it comes down to, okay, so a sufficient condition for serializability. Every cycle of the DSG, so every time you form a cycle in the DSG, is free of dangerous structures. Then it's conflict serializable, right? So if every cycle that you look for in the building up DSG, right, if they're free from dangerous structures, then it's conflict serializable. Okay, now there's some kind of definitional things. I mean, I haven't implemented this algorithm myself or kind of played around with it, so it's kind of hard to get a good intuition about why this is the case. But these are the conditions that have been built up now that will essentially define this the first cut at this serializable snapshot isolation. This is an active area, so these conditions here are fairly. They're probably overzealous in terms of detecting what they think a dangerous structure is, and then aborting transactions. But at least it's going to guarantee that they are conflict serializable. All right, so here's just a simple example of that right skew example we had from before. So we look at the DSG here. We have a cycle here, and we have two consecutive. We have a dangerous structure here because we have a read-write followed by a read-write. Okay, this is on Y, this is on X. So it shows that it doesn't matter what the data object is. We see here a cycle in the DSG that is a dangerous structure. Okay, therefore, this is the dangerous structure. Therefore, we need to pick one of these that are going to get aborted. Right? So that basically is showing that we can get this. We can detect this in the example in the right skew example, and that whole example of that kind of like rotating ring of objects that you'll if you think about it, you can see that happens there as well, because they're all kind of read writes. In fact, in that case, it's quite overzealous, and it would probably kill one that doesn't have a ring. That it's just by the fact it's doing that. So that also shows an example where it's being overzealous. If we have just all the data values set up where we're just doing copies from, they're forming a line rather than a ring. And there is actually a serializable schedule, but still there'll be dangerous structures there. So it's probably going to, I guess maybe the condition with it being a cycle means it so that they will actually let that through. So I have to think about that. But, again, I don't have strong intuition about this because I haven't implemented or played around with it too much. But there's notions of these. There is a. At least, I mean, you can have a very, very aggressive notion of a dangerous structure, so that if you just get any of these two things in a row, that you'll destroy it. Now, I know that Steve was the one who developed these slides here for this. I know that he was doing actually research in this area, looking for better algorithms that kind of approach more the truth of how that were the most permissible. They allowed the first bunch. They were very reluctant to abort transactions, but the implementation gets very complicated essentially. All right, so so it's under active development. I'm not really sure what's going on in PostgreSQL with this, but they do have serializable snapshot isolation implemented. So you look for these dangerous structures. When such a structure is fine, you choose a member of the transaction as a victim, you abort it and rerun it. So this potentially, maybe I should cover this slide first. The potentially dangerous structures are just basically two consecutive vulnerable edges. So they don't need to occur in a cycle. So that actually solves the problem. So in that ring example, if you do have a line, then you'll have basically, not in a cycle, but you'll have two consecutive, you'll have dangerous structures, right? You'll have two vulnerable edges, read writes in a line, and then it will just basically have to pick a victim. So it'll definitely be overzealous in that case. A algorithm that's a bit more advanced is actually looking for true loops. It's more computationally expensive and more complicated to implement, but it's going to be closer to the truth. That's probably what they implement actually in PostgreSQL, something that actually will look for the cycles and go all the way through. So this is kind of recent work in transactions. Okay, so serializable snapshot isolation in real systems. So until very recently, all the 5 major databases: Oracle, Microsoft SQL Server, PostgreSQL, MySQL. Of all of them, only SQL Server and IBM have provided true serializable mode until recently. That's because they're based on lock-based kind of single value concurrency control implementations using two-phase locking. But as of version 9.1, the serializable, okay, now finally in PostgreSQL 9.1, they implemented this serializable snapshot isolation, some variant of it at least. So now it is truly serializable when you run that isolation level. So what they've done in PostgreSQL is that repeatable read. So basically, when you set the isolation level, like using the old keywords, basically the way it works is this. Let's say I hope that we have this here. So no, we don't. Yeah, here we do. Yeah. So in PostgreSQL, basically it's kind of a bit. Some people kind of run into this because they say, well, read uncommitted and read committed, they actually behave exactly the same in PostgreSQL. And what they're doing is they're just doing and repeatable read. These are all doing the same thing if you put them into PostgreSQL to find isolation level, so they don't change. They're basically implementing the snapshot isolation, which allows for these anomalies, these right skew anomalies. All right, so this is this is, but then read uncommitted and repeatable read are really not natural in MVCC. So let's just kind of say what we look at here. These are okay in PostgreSQL. How do you actually do it? So when you begin a transaction, you set the transaction isolation level. You can set it as serializable. You can set it as repeatable read. You can set it as read committed or read uncommitted. Okay. So if you set it as I should actually have something on the slide here that kind of spells this out. If you set it as, let's say you set it as read uncommitted or read committed, that's going to give you snapshot isolate. That's going to give you read committed isolation. Right. So that's this read committed that multi-version concurrency control read committed. That's what you'll get if you said read committed or read uncommitted in PostgreSQL. If you set it as repeatable read, okay. If you set it as repeatable read, then what you're going to, I'll fix this in the slide. If you set it as repeatable read, then what you're going to get is you're going to get the snapshot isolation, the classic snapshot isolation, which allows for the right skew anomaly. If you set it as serializable, then you're going to get serializable snapshot isolation. So this is all true now for PostgreSQL version 9.1 or greater. This I'll fix. I'll fix this in the slides because it's not a very good description here. Just kind of intuitively what happens. I'm assuming everybody's going to be running PostgreSQL 9.1 or beyond. So that's a given. All right. So when I go over the recitation, which I'll just do right now, I think this will be a little clearer, kind of what you want to do in the actual. Let's see here. Let me just see anything more I want to say about all this. Yeah, I think it'll be clear when I show the recitation. But I'll just make one last comment here. This is probably worth saying. So there are two general modes of transaction initiation. Okay, session-based. So SQL statements are executed one after another, but commit only occurs at the end of the session with an explicit commit directive. So actually, this is the default in Oracle. But the idea here is that, statement-based is usually kind of what you're already doing. So implicitly, you're always doing a begin and commit when you average a single SQL statement. But if you say specifically begin transaction and then do your SQL, then at the end of that, then you basically say, well, you can be reading, you can make all these changes to the database, do these reads, and say, okay, yeah, commit, right, or abort or rollback. So this actually is quite useful. So like if you have a system where you're going to go through and you're going to make a lot of changes to a database to fix it up, this is very common, right? You have a database that's kind of in a junky state, and you need to go through and do a bunch of reads and writes on it to kind of make it, to kind of like do deduplicate data is something. So you see that, oh, that tuple and that tuple are actually the same. They're referring to the same thing. They have a different ID because of some reason. So I've got to do some operations now to kind of bring them together in the database, right? Because they mean the same thing, and then so other referencing tuples have to kind of be brought into agreement, and that could be, you know, a significant kind of working of the database. Now you do that, and then you screw up, and you basically, oh, I just made a big change. I want to abort this because I'm screwing up the database now. I do not want to commit this to the database. So just then, if you're doing it as a transaction, say abort, right? And it just backs you off. So the database gets restored to what is previous, to whatever its state was that you started the transaction. Or you fix it, that in the data, you do the deduplication or whatever it might be, and then you say, okay, everything looks good, commit, right? Even with that, you might want to do some kind of checkpointing where you're copying the database in backup, so you can, you think you did right, but then you commit, and then actually you want to reverse out of that. So you need to restore from a previous checkpoint. But that just shows that even as the single user, having transactions sometimes is useful because of the potential to kind of back out or abort. So that's kind of at the SQL level, kind of, if you commit, you begin, and then you do a bunch of work, and then you commit. All right. So that's kind of this session-based approach. All right. So that's quite useful. All right. So let's look at recitation. Oh. It's weird because I have to change this. No, I don't. All right, so I'm going to bring in this recitation. So recitation number 3. And I'm going to get rid of all these things. One sec. Bear with me. Yeah, there we are. Okay. Okay, I trust you guys can see this. Make it move a little bit bigger. Okay, yeah, I think I should go over recitation a little bit here because before I should have done this with the indexing one, because then I would have told everybody you got to build indexes or put some conditions on that. But, so anyways, right. So these are the paper problems that I want you guys to do. These are pretty straightforward, I think. So given this schedule here, what is the direct serialization graph? So draw out the graph. Is it conflict serializable? Don't see my chat. So chat has disappeared for some reason. I don't know why that happens, but it does sometimes. And so in other words, unmute yourself and interrupt me verbally at this point, because I can't see the chat. It went away. What? Yeah, it went away. I'm using an old version of Zoom. Or maybe even the new version does that. I don't know. All right. So like things like paper problems. So is this, okay, like look at this schedule here. Is this conflict serializable? Is it view serializable? Okay, so it just kind of makes it so that you work with the definitions of these things. All right, this is something that might be, okay, assume the following schedule with locks is executed over a SV, so the classics, single value concurrency control, single version concurrency control. Does this respect 2PL? Is it two-phase locking? And then these definitions is rigorous and conservative about releasing, grabbing the locks, all the locks at the beginning or releasing all the locks at the end. All right, so, and then also then describe what happens as you're going through this, describe what happens as these are executed. And what I mean by that is like, think that you're a concurrency control mechanism that's controlling access here. So assume the operations for if one operation, if one transaction gets stuck, so if they're waiting on a lock or something, then just let the other transactions in the schedule then resume or continue, right? So if somehow or another, like one of these gets, like transaction 2 gets blocked somehow because of a lock request, waiting on a lock, and there's more operations, in the schedule that are transaction 1, so 2 got locked or is waiting, and then there's further ones along the line that have transaction 1 doing something, then go to those. Assume that transaction 1 and transaction 2 are in parallel, right? So that if transaction 2 is waiting, doesn't mean transaction 1 will be waiting. So the way these actually get reflected, so in other words, the above schedule presents the order in which the operations are queued over the single version concurrency control mechanism, not necessarily the order they get executed in, right? Okay, so then we get to this. This is actually probably what was kind of important here, was this, all right, so it's got to be version 9.1 or greater because we need to have serializable snapshot isolation. And consider we have the concurrent transactions of the following form. So in this case here, we have, you're going to set the isolation level to X. And this is over a database that just has the accounts here. And then you're going to do it under read committed, which is basically going to be giving you read committed under MVCC. Repeatable read, which is going to give you just like the classic snapshot isolation, and serializable, which is going to give you the serializable snapshot isolation. So using these terms here, these keywords here, up here for setting the isolation level, that's going to give you the mechanisms that correspond to what we covered today, right? The three mechanisms: read committed, snapshot isolation, and serializable snapshot isolation all get, they all get set by these keywords. All right, so I want you to do that. This is kind of interesting right here. This will show you, this actually is the story of that, of some, I guess this, I don't know much about the exacts of the story, but apparently there was, all right, so basically that, what it sounds, so this is my understanding. So again, I don't want to be quoted on this because I don't know the details of what happened in the industry, but my understanding is that a lot of databases, because they wanted to perform better on benchmarks, because it's competitive out there and you got to perform better on benchmarks, a lot of them were defaulting the concurrency, their isolation level was defaulting to read committed, because you do better if you're under read committed. I mean, performance gets better if you're under read committed than like serializable snapshot isolation is going to be more expensive. It's going to be, you're going to get less throughput. Anyway, so they were defaulting to that, apparently. This is the story I heard. They were defaulting to that, and then to get better marks on benchmarks. So, but the thing is that apparently, I mean, I shouldn't laugh, but apparently there was some Bitcoin exchange that just kind of ran the thing out of the box, and it was running under read committed. And based on that, what this shows right here, under read committed, if you do that, you can bankrupt the exchange. So you can have something that basically says, I can transfer money from one account to another account, or coins, Bitcoins, whatever it is, from one account to another account. But I can launch a whole bunch of simultaneous transactions under read committed, because that's what they defaulted to. And basically what will happen, even though each one is checking to see that the account doesn't go low. In fact, because I go under that isolation level, I can basically just put all the money into one account, and then all this debt grows in the other ones, even though it wasn't supposed to, or all the debt grows in the other account. And then, of course, you'd have to do very quickly, then grab the money from that and do a exchange out to some other remote party to grab the money, and then just leave a bunch of debt in that one account. Apparently, that some variation of that was what bankrupted one of these Bitcoin exchanges. So because they didn't run under snapshot, they ran under read committed, so they got in trouble. So you'll kind of do, you'll verify that here in this particular problem. And then these problems here. Okay, so two transactions. Yeah. Okay, this is yeah. Then I want you to create deadlock here. I want you to go through and manually kind of create a deadlock, so you can see what happens when you deadlock two transactions, and see what PostgreSQL does about that. So this right here is what I think is probably we're talking about. Okay, so this right here is going to basically show that we can have a practical. We can have an example here of runways. So if we're doing booking, this is kind of an important thing. I mean, we're going to be booking runways for flights, for planes to land on in different time slots. And we want to have this, we're going to have this kind of right skew kind of thing where we want to basically have a trigger that guards against allowing two flights to be booked on the same runways in consecutive timestamps. We would like to space them out a bit. And what this shows, is what you'll be able to see here is you'll be able to see that you're actually able to get, because of the rights, this is basically the right skew anomaly. Under snapshot isolation, you're actually going to have it, even though you have that rule in there, you're going to actually be able to construct a situation where two plans land in consecutive timestamps on the same runway, and that could lead to like serious trouble. So this is a kind of a vivid, I'm trying to create a vivid example here of why you want to run under serializable snapshot isolation, which would then prevent that. So it doesn't let the controller book that runway where it could potentially crash another plane. Yeah, so that's kind of a vivid example of that. And then you also get this also is going to show you a little bit, give you some insight into what the locking granularity is, in PostgreSQL. Because, yeah, all right, okay. Anyways, I'm glad I just went through that just to kind of to kind of maybe set up what this recitation is about and how it relates back to the lecture. Okay, so are there any questions at this point? Because I think we can stop for today. Don't put them in the chat because my chat disappeared for some reason. Maybe I can get it back if I do this. Yep. Okay, now I got my chat back because it's silly thing. Okay, this recitation is going to be in exactly 1 week. So next Tuesday. I always give you guys a week to work on recitation. So exactly 1 week from now, next Tuesday. Then the Friday after that, then we're going to have the lecture on data exchange. And then I think I sent out an email earlier saying what the remaining schedules of the course. So data scraping, data exchange. I mean, a little bit with no structures. Yeah, the date on the final quiz. I think isn't that already set? I mean, doesn't that? I mean, that doesn't show up on your guys's. I'll post it on Canberra. I thought it should show up by now. I've had that date for a while now. But anyways, I'll put that. I'll post that up there. Yeah. I think it's the 1 week after the last lecture or the final lecture. Yeah, I'll post when the quiz. Yeah, it'll be on camera. Yeah, good. And then the final quiz will be it'll just be kind of like recitation problems. That's what it'll be, recitation problems, and it'll be open book because I can't run it any other way. Not in the COVID times. Well, technically it'll be 4 hours. The question is how long it'll be, but it won't take that long. I mean, it's mostly just to get you guys to kind of run your eyeballs over these stuff one last time and kind of sink in. It's only worth 100 points, by the way. So it's not that. It's just mostly just to kind of get you guys to do one last reflection review of the material. Yeah. Okay. Well, if there's any other questions, then no, you do not have to register for the exam. No, it'll be through Canberra. That's right. It's not obligatory. If you want to skip it, but you're going to lose 100 points. So if you want to get a 5 in the course, then you almost have to take the exam or the quiz. But if you want to skip it, you can skip it. Good. That's the spirit. I had somebody saying that they're going for a 5. They say, yeah, they're going to do it because they want to get that 5. That reminds me of my undergraduate days when I myself was once accused of being a greedy, grubby grade grabber. It was just kind of, I don't know. In Sweden, I don't find it. In the University of Michigan, we were really, I almost got slugged by some guy at an exam once because I was finishing my exam and I think I looked pretty happy or something because I thought I did really well. And he was competitive, but kind of pointless. But still, it's nice to get a 5. It's good to be. There's a certain joy in being fanatical about these things. So, okay, well, I think that will do it then, and I will. Yeah. So again, project leaders, send me at least some status message on your projects, and then maybe we'll have some meetings, and then I'll see you guys next Tuesday for the recitation. Okay. See y'all.